So this is a video to tell the difference between magnetic flux density, magnetic flux, and magnetic flux linkage. So magnetic flux density, which has the symbol B and is measured in the unit Tesla, is about how strong the magnetic field is. You can see this is a weak magnet, this is a strong magnet. And the field lines are very close together in a strong magnet and further apart in a weak magnet. That's pretty simple. So then magnetic flux is phi, measured in Weber, and that is equal to B, which is the strength of the magnetic field, times the cross-sectional area, times cos theta. And it's the number of field lines passing through an area. So I've drawn the magnetic field here in a sense that you're going to pretend that these are giant magnets, and you're standing in between them. So if you were standing with your back to the North Pole over here, you would see all the field lines going in to the edge of that magnet. And it's going to be like this. So there are lines going straight down. The magnetic field lines are going straight down into the page, like that. All right. So how many field lines pass through an area? I've got a little thing from my kitchen which helps to open bottles that are hard to open. So I'm going to let that be my loop that causes the area. So my number of field lines passing through an area on the weak magnet, you can see it's not many. If I put that same area down on the strong magnet, I've got a number of field lines passing through the area is much bigger because it depends on B, the strength of my magnetic field. Okay, so that's like that. Now looking at the area, if I change the area of my loop, I've got fewer field lines passing through that loop. If I put it onto the weak magnetic field, I can increase the area. I've got more field lines passing through my loop. So magnetic flux depends on the strength of magnetic field, the area of your loop, or the area that the field lines are passing through, and then it depends on the angle, cos theta. Now this can be a very confusing angle, but it's not that bad. We say that theta is the angle between the normal to the surface area of the coil and the magnetic field lines. So the surface area of the coil is that. So the normal would be like that. And I'm interested in the angle that the field lines are to that normal. So maybe showing you more closer to like that, so you can see in the middle there. Let's only choose one of the strengths. So the field lines are at the moment parallel to the normal to the surface of this area. There's the surface, the normal at 90 degrees to that, and the field lines are at 90 degrees to that. So I beg your pardon, the field lines are parallel to that normal. So the angle is actually 0 degrees. Cos of 0 is 1. So here we actually have the maximum number of field lines possible passing through this coil. However, if I start to turn this coil through an angle, my normal turns with it. Okay, I've now got an angle to that coil. Can you see that the number of field lines passing through is getting smaller and smaller? Okay, as I turn it, the number of field lines getting smaller and smaller. Here goes my normal to the surface. Now my coil is actually parallel to the field lines. My normal is sticking out to the left like that. I have 0 flux, 0 lines passing through my area. And now the angle between the field lines and the normal is 90 degrees. And cos of 90 is actually 0. So that is why my flux is 0 when my coil is actually parallel to the field lines. Take it back. Now I get my maximum number of field lines, my maximum flux. Now, when Faraday's law speaks about rate of change of flux, the EMF induced is proportional to the rate of change of flux. You actually, now if I want to change this flux, I start spinning it. The flux is changing all the time. There's the maximum, getting less, going to 0, getting more, going back to another maximum in the other direction. So I'm spinning this thing, changing the rate, changing the flux, and my rate of change of flux, I can increase that by spinning faster. Now my rate of change of flux is greater, and my EMF induced will be greater. Have I got anything I haven't said there? I think that was okay. Then if I move up to the concept of flux linkage. Flux linkage is the product of the number of turns in the coil and the flux. So if I have a coil, it's going to have a certain amount of flux, a certain number of lines passing through that coil. And if I have several loops, so if this was a single wire that just got coiled and coiled and coiled and coiled, I'd have several of these loops, and every time I have a rate of change of flux, it actually does that for every single loop. So that's why our flux linkage is increased by having a greater number of turns in the coil.